So today we're going to be looking at how designers actually design real columns in practice. So we've been talking a bit about the theory, starting off with the completely elastic Euler load or buckling load pi squared EI over L squared. We talked about real imperfections, or that column members are not completely perfect. They may have an initial camber. They have got residual stresses locked in. They're not perfectly plumb. So we've talked about those things. And then yesterday we brought in the idea that we somehow need to be able to handle the yield stress or the material properties of the column. So today we're going to be talking about design standards. So the design standards like the Australian, New Zealand design standards, say for light steel, which is 4600. If you design a column to 4600 and if that column fails, the idea is that you are not responsible. The engineering community which put together 4600 then becomes responsible for that design. So that's codified design, and that's where we're leading to. We're leading to you guys having an understanding as to the background of the codes, because the design codes which you'll be using as engineers when you work in practice in design offices, they're full of equations, and as engineers you need to, as practicing engineers, you need to have an idea as to where these equations come from so that you can comfortably operate the equations or comfortably operate within the design standards. So yesterday we brought in the idea of the yield stress, which you can see there, sigma y, and why we're interested just in sigma y and we're not really interested in sigma u, and that's because of that horizontal plateau that goes along there. And then we talked about how to convert the Euler curve by dividing it by the area to turn that into an elastic critical stress. And then on this axis here, we've plotted the length. And then we've said that we can draw this graph here, and you can see the material is going to be limited by its yield strength along there. So it can't take more stress than its yield stress, of course. That's for short columns, and then for long columns, which you can see down there, that would be the behavior according to Euler. So that covers the material. A column can't take any more stress than its yield stress, and a column undergoing buckling, that would follow that curve there. So if we now say that's our stress for the yield stress, and at that point it intercepts the Euler, and then from there we go down, trace the line down there, we could say that that becomes a sort of an upper bound to behavior. You know that a column cannot take a load more than its Euler load, and you know that a column can't take a load more than what would cause its fibers to yield under compression. So you could sort of trace out that with a very sharp point and then suddenly move around there. So a bit of common sense about how the real world operates should tell you that a real curve like that is not really what's going to happen in nature. So this axis here effectively being the length, and this axis here effectively being the strength, being the stress, some sort of discontinuity or some sort of point here where suddenly it follows that behavior isn't exactly what's going to happen. So a bit of understanding how the real world behaves would lead you to appreciate that a real column is probably, that being the length axis, a real column curve is probably going to be more rounded by that. It's going to be more rounded like that, and it's this sort of curve which you will find in the design standards. So the design standards would define a curve that goes around there, and all you really need to do is to work out the slenderness and then read off the stress value here, and then you can design that. You can design your real column quite comfortably. So the question is, firstly, how do we get an equation that can represent that? All the major design standards these days have used what's known as the Perry-Robertson equation. So we'll show the Perry-Robertson equation a few pages further along in the course notes. But before the Perry-Robertson equation, and please remember the Perry-Robertson equation is just a fit to experimental test data. It's like saying we're just passing a line through experimental data points. And before the Perry-Robertson equation came along, developed of course by Perry-Robertson, engineers may have been using what's known as the Rankine equation. So remember at this stage, important thing is that line is theory, sigma y is theory, that line there is theory, but when we talk about Perry-Robertson or when we talk about Rankine, which we're about to, it's not theory, it's just a curve fit to experimental data points to allow you to get a smoother curve that does fit the experimental test data. So let's talk about Rankine first. So I suppose it's Lord Rankine, and I can't remember which, but I think he's from Belfast, and then he went off to Glasgow University. So I've seen his statues in the parks when I walk by. Rankine, so you can probably Google, which I won't at this stage, but maybe he was around the 1800s or early 1900s, I'm not sure. But you can see it's quite an old idea. So Rankine proposed a simple formula for stress at failure, which was one of the oldest formulas used for column design. So again, re-emphasizing, we're now talking about design. We're talking about design standards. We're talking about what engineers will be doing in the design office when you will be designing a column. Note, it's no longer in use, having been replaced by the Perry-Robertson equation. But it does provide a good illustration for this problem at hand. So what Rankine said was that if he takes 1 over the failure, that is going to be equal to 1 over sigma CR, which is from pi squared EI over L squared, plus 1 over sigma Y. So he just came up with that, and it's not bad as a starter. 1 divided by the failure load is going to be 1 divided by sigma CR plus 1 over sigma Y. So if you get a very, very short column, your sigma R or your sigma CR is going to be very large, so that value becomes 1. And if you've got a very, very long column, again, 1 over sigma Y plays part of it, and then you've got 1 over CR for the long column. So it's got the desirable property that the failure stress sigma fail. So let's see if that's graph there. No. It's got the desirable property that the failure stress sigma fails tends asymptotically to the yield stress. So again, that's probably what I just said. For very short columns, your sigma fail will be very similar to sigma Y, and for very long columns, sigma fail would approach sigma CR for long columns. So the curve described by the Rankine formula is very similar to the solid line shown in figure 14. So we'll draw that again, even though it was just across the page. So I'll put a dashed line there. So we'll call that sigma fail, and then we'll call that sigma Y on that axis there. And then we'll have the other line going like that, which would be your Euler, or that would be sigma CR. So the Rankine equation for small values, so you can test it, it would approximate that point. For short columns, and then for very long columns, it would approximate that point. Okay, so for small slendernesses, it agrees with sigma y, and you can test the equation to find out. And for long columns, it approximates sigma cr, and you can test that equation if you can't see it, obviously. And how the curve goes is that it might go like that, and then for a very, very long column, it becomes asymptotic to the sigma cr. So that might be the shape of Rankine, or what Rankine would have defined as sigma fail. So that's not bad. These equations, of course, need to be tuned, and there's a tuning factor. And the tuning factor, to tune the equation to best fit the experimental test data that's available. So for example, University of Auckland does some tests, you do some tests at University of Canterbury, you do some tests somewhere else in the world, and then you get some data points, and then you just want to be able to pass the Rankine curve right through the middle of those points, because obviously with experimental test data, you will get some scatter. So there would be like maybe 1,000 experiments that have been done on steel columns. Somebody would have put that into a graph at some stage, and then you would be trying to pass a nice curve that goes through right through the center of those points. And you can control it. You can control the curve, whether it's like that, or whether it's like more like that, or whether it's more like that. So you can control the curve on your spreadsheet with the tuning factor. So that's probably more evident in when we see the Perry-Robertson in a few minutes. So these crosses here would be experimental test data. So anyway, let's go back. So we can look at the Rankine formula, and we can rearrange the Rankine formula as sigma fail equals sigma y, 1 plus sigma y divided by pi squared multiplied by e times your lambda squared. So that's just a rearrangement of the Rankine, and we've got this thingy here, and we can call that A. So we can call that thing A. So the ratio sigma y divided by pi squared e is denoted by A, and can be adjusted or tuned like a car mechanic or someone trying to tune the Rankine curve to pass right through the middle of the experimental test data. So the ratio is denoted by A and adjusted to take into account the empirically observed buckling stresses from laboratory test results or observations, and with these modifications, sigma fail is equal to sigma y 1 plus alpha lambda squared. Sorry, 1 plus a lambda squared. Then you would say the compression failure load of a column can thus be calculated as NC is equal to sigma fail times A. So you work out your sigma fail, multiply that by the cross-sectional area, and we've got the load at which the column, we've got the load that the column can carry. So it's not up to you as an engineer. So let's suppose Perry-Robertson hadn't been developed to supersede the Rankine. If that hadn't been the case, then the design standards like 4600 for light steel, that would tell you what the value of A should be. So that's not something that you guys as practicing chartered engineers need to do. That's a responsibility carried by the profession, and someone in the profession has tuned that curve. So if you follow everything else correctly and your column fails, you are not responsible. The profession is responsible because the profession has come up with the value of A, and what you've done is followed it using using best engineering, using your engineering judgment. So of course you can't do a stupid thing like, say I'm designing a timber column and I'm going to be using the value of A from my steel standards. Of course that's not permissible. But if you were designing a steel column and there's nothing particularly strange or different or difficult about it, and you take A from the design standards, the profession takes the responsibility should there be a disaster and that column fails. So let's have a look at a design example. So example number 5. So a 200 by 200 times 5mm hollow box section is 5 meters high. So here is your column 5 meters high. We've fixed the column at the base, so the base of the column is fixed, and we've propped the column at the other end, which you can see there. So you've got your pin condition there, and then you've got your fixed condition at the bottom. It's made of steel. The steel has a yield stress of 300 megapascals or 300 newtons per millimeter squared. What load P would cause the column to fail according to the Rankine formula, with A is equal to 0.9 sigma y divided by pi squared E. Okay. So A has been given to you. So you can see that the tuning is just applying a 0.9 factor to that A. Compare this to the Euler buckling load and the squashing load. So the Euler buckling load, of course, is pi squared EI over L effective squared. So L effective is not equal to the length in this case because it's a fixed pin condition, as we talked about in previous lectures. And compare this to the squashing load, and the squashing load is when the fibers fail because they reach their yield strength. So that would the squashing load would be the area of the cross section multiplied by the area of the cross section multiplied by sigma y. Okay, so that would be what's known as the squashing load. So, and you can see that I reuse this as the 2017 exam question. Effective length, L effective is equal to 0.7 L. So you would know that from what we've done before. So if we flick back through the course book, at the start of the buckling, we've got effective lengths of the columns. So the effective length of the column is 0.7. And because the condition is pin fixed, 0.7 multiplied by L, and you will get 3.5 meters. Section properties, these are given to you. So in this country, maybe you're buying this section from New Zealand Steel. If we look at the corners, maybe when they did the corners, you can see there's some roundness to the corners of the box section. So we don't really want to be having sharp corners because you end up with stress concentrations. So manufacturers like New Zealand Steel, they will say we sell box sections, they're 200 meters by 200 meters by 5 millimeters thick, and they will tell you the section properties. So if you try to calculate A using these dimensions here, 200 times 200, subtract that smaller one there, you're not going to get this A. So this A would be calculated taking into account the roundness or the radius around the corner of the box section. So students in the past have tried it and they've said, why aren't they getting that number? And the reason why they're not getting that number is because this number may be coming from a manufacturer's catalogue. Again, the manufacturer's catalogue would have been signed off by a chartered professional engineer. So you've been provided with A and you've been provided with I. So next thing is to work out the radius of gyration. So the radius of gyration is the square root of I divided by A, which is 0.0796, and just note the units, it comes out as in meters. Then you work out the slenderness. So we know that slenderness, which would be on this axis here, is going to be equal to the length of the effective length of the section divided by the radius. So the effective length of the section is going to be 3.5. You divide that by r, which you've just calculated, and we worked out that that's a number 43.9. So later on, when we look a few pages away, if we read off the 43.9, you can probably tell that's in the short column region of the Perry-Robertson curve. So that would, the slenderness of that value would be considered a short or a stocky column, and a slenderness there would be a long column. Then Rankine's A is 0.9 of sigma y divided by pi squared e, and then that one has been calculated for you, and that works out as 136.78 times 10 to the minus 6. E is probably 200 times 10 to the 3 newtons per millimeter squared for steel. So sometimes they use a larger value. In Europe, they might use 210 times 10 to the 3. Sometimes they use 2.05, but it's just around 200. So whether it's 200 or 210 doesn't really make too much difference. So the Rankine failure stress, which you'll get by just using the Rankine equation, you get by plugging all those numbers in, and you end up with 237.3 megapascals. So that would be a stress, and of course a megapascal is 200 newtons per millimeter squared, and that we know that the yield stress is 300 newtons per millimeter squared. So it's always nice to have a bit of a reality check and just compare the failure load against the yield stress. So the Rankine failure stress is just a bit lower than the yield stress. The Rankine failure load is therefore the cross-sectional area, so the gross cross-sectional area of that, so 3.9 times 10 to the minus 3 meters squared, multiplied by the stress, or the Rankine failure stress that you've just calculated, and that turns out to be 925 kilonewtons. So let's just now compare that against the Euler. So the Euler is 398 obtained by pi squared EI over L effective squared. So you get 3948. So 3948. And then the squashing load is going to be the area times the yield stress. And that's going to turn out to be 1170 kilonewtons. So we can see that Rankine has predicted a squashing load slightly less than, has predicted a failure load slightly less than the squashing load, and much less than the buckling load. But obviously the effect of buckling has reduced the design capacity at 925 because it's less than the squashing load. Put this another way around, if it was all in tension, then you would expect the Rankine failure load to be the same as the squashing load, assuming of course that the yield stress and the ultimate stress are the same. So that's really the effect of buckling. The effect of buckling for your design is the difference between the squashing load and the Rankine load. So as can be seen, the Euler solution overestimates the compression capacity of this short column by as much as a factor of 4. So you wouldn't have been wise to use Euler. compared to the squashing load, Rankin's solution takes into account the non-elastic buckling and is lower by 21%, which is a significant reduction. So if that was the slenderness on the, so if that was the sigma fail or the sigma design, what you would be doing in the design office, and that had been the length or the slenderness in that case, what you would have calculated for the failure load would be 21% less than the squash load. So this hasn't been that a difficult calculation, but just again re-emphasize that the Rankine formula is tuned to the experimental test data, and the profession takes responsibility for that tuning, not you as an engineer, as long as you're making sure that what you're doing is not out of scope of the design standards. And then once you can do that, you can do very quick calculations to work out the loads at failure, or the design loads at failure.